Hello everyone, this video is about single, and I am still on a race, single displacement reactions, which are very similar to double displacement, except one element replaces another element that's already in a compound. And then, so basically, so say you had A plus BX, and A was a metal. These two are going to swap places. You're going to have B plus AX. And then say A was a non-metal. These two are going to swap, and you're going to have X plus BA, because always write the metal first. So metals, more reactive metals, replace less reactive, or less active, not reactive, active metals, and then same thing, more active nonmetals replace less active nonmetals. So as always, positive go with positive, negatives go with negatives. So, but what this active means, if you look on your solubility rules chart, at the top there's this thing called activity series, and it lists a bunch of metals and like 6 nonmetals. And basically what that chart is saying is the farther left on that chart, the more active, more reactive those elements are, and they could replace anything to the right of them. So lithium is the first thing listed. Lithium can replace any of the metals because it is the most reactive. But if you take calcium, calcium can replace sodium because sodium's to the right calcium, but calcium cannot replace potassium because calcium's less reactive than potassium. Potassium can replace calcium, calcium can't replace potassium. And then remember, for those nonmetals, that equal sign is not saying everything on the left equals everything on the right. It's saying that bromine and oxygen have about the same reactivity level, but at the end of the day, bromine is a little more reactive. So if you had to choose, but that's just saying those are pretty equal. So like fluorine can replace any nonmetal, sulfur can replace any. So that's what that activity chart is. And so that's kind of all there is to single displacement. So like chlorine gas reacts with potassium bromide. So the way we write this is we're doing the molecular chlorine. Remember, chlorine's a Brinkelhoff, so it comes in 2. Gas plus potassium bromide, which is aqueous. I always forget the little A. Aqueous. And then remember, you have to protect your products. So the chlorine and the bromine are going to switch. So you're going to have potassium chlorine, which is aqueous. And then you're going to have bromine by itself. And bromine is a liquid. Just a note, I guess. I'll write it down here. Bromine and mercury are liquid. At room temperature. So just remember that if you have to write it by either of those by themselves. All your nonmetals, for the most part, are going to be gases. All your metals are going to be solids. But just remember that. And then, as always, just balance it out. Oh, remember, bromine is also a Brinkelhoff. I forgot that. So you need to have that 2 there. 2. It all balances out. You can write a total ionic, that's the molecular. The total ionic equation would just be chlorine to gas plus 2 potassium aqueous plus bromine aqueous gives you 2 potassium aqueous chlorine aqueous plus bromine 2 because it goes together with itself aqueous, that is A. My A's and Q's are very similar. And then, of course, you get rid of the spectator ions, which in this case is, the only one is potassium, because it's the same on both sides. And that gives you, so basically what happened in this reaction is we had chlorine gas, 2 bromine ions, and they combined, or they didn't combine, and that happened. This looks surprisingly similar to a redox equation, which I will talk about in a different video because that is a whole other can of worms. And so this is basically all for single displacement. I'm going to try and chunk the videos up into the types of equations so you don't have to watch like an hour-long video because no one wants to do that right now. So yeah, this is pretty simple. Of course, if you have any questions, need more practice or anything, feel free to talk to me. Yeah, that's literally it. So, thank you so much.